third workshop. Today we will talk about the evaluation of the coil conductor modeling that we started last week. We had like these three different ways of model the coil conductor. Then we're gonna, I will show you how to export scattering matrices and electromagnetic fields. Karthik helped me with that. And then we will also do co-simulation for single coils and arrays. Also Karthik showed me how to do that. And then we will, maybe if we have more time, we will go like into scripting and HFSS. So first about the coil conductor modeling. If you remember, last time we did this, our very simple model that we were working on since the first workshop, and let us just see how it looks like. View, hide in all views. So this is how our simple model looks like. We have a loop coil and loaded by a spherical phantom. And in the simplest example, we just assigned the coil conductor perfect electrical conductivity. So this is the simplest thing to do. Also the computationally least expensive. So this is going to be the fastest. But also it's not that accurate because we know that coil conductors have some loss. And the next level of like modeling the loss would be to assign that coil conductor finite conductivity, and then we assign the conductivity of copper. And to be honest, I'm not exactly sure how the software is modeling that, but we can have a look at that. And then the last step, the most precise, hopefully, is to thicken the coil conductor by the thickness of the copper, which is only 35 micrometer. I don't know how thin a hair is, but probably much thinner than that. And if we zoom in close enough, we can see that the coil conductor has this thickness. And I hope you guys can see that. You see this edge, like that's the thickness that we assigned to it by thickening the sheet. So now let's just, unfortunately we don't have a validation. It would be best to have like a measurement for validation, but we can hopefully see a difference between the three different ways of modeling it. So let's just create a modular model solution data report, Smith chart, new report. Or maybe Z parameter would be the easiest. Karthik, can you mute yourself, or should I mute you?
What is that?
Can you please mute yourself for now?
Sure.
Thank you. So we can add a marker here on the solution, and we can just copy this value. So perfect electrical conductor, we have a reflection coefficient of 0.29.11 and imaginary part of 6.871 times I. Then the next more difficult way to model is the finite conductivity, and there, let us have a look what that looks like. So that's finite cont 0.2973, so it's already different. You can see by adding like a finite conductivity to the sheet, we're gonna change the result. And then last thing was the thickened sheet. And let's have a look at the result there. No, that's rectangular. Create Smith chart. And then we can add a marker again. Two, 4. Plus 6.87. So we can see that all the results are different, so that's a good sign. That means something is happening. Yeah, unfortunately, I don't have anything to validate it with, but we can have a quick look in MATLAB how about the magnitude of the S parameter, because that will give us a sign of how much energy is reflected. So for the tech conductor, oh, we can see the magnitude here directly. And I didn't write down the. So the magnitude for the thickened sheet is 0.0987. We can see it here on the top. For the perfect electric conductor, I expect a higher, probably a higher reflection coefficient because there is less loss, and 0.988, so it is higher. And for the finite conductivity, I expect something closer to 0.9878. So forget about these results. I don't think I copied that right. But the absolute value of the reflection coefficient, we can see that. Sorry, I mixed it up. This is right. We can see that for the perfect electric conductor, we have the highest reflection coefficient, the magnitude, and then it goes lower for the finite conductivity and for the thickened sheet. But yeah, we need to have like some validation. But you see, like there, these are the things that you can like play around with in HFSS. Yeah, and note that for the perfect electric conductor, although the result is not is the least precise of all, but it's the fastest computation. So if you need to have like a quick simulation run, then you can just assign perfect electric conductor. But thickened sheet will give you the most precise result. Is there any questions for that? If not, then let's go to the next point. That's the export of scattering matrices and electromagnetic fields. If you want to process the results that you got from HFSS further in MATLAB or ADS or for plotting purposes, then you can export the results. So for the scattering matrices, the easiest thing to do is right-click on results, select solution data, and then you have matrix data here, and then you can click here the export tab, and then just select export matrix data, and choose the proper project directory. I'm just gonna save it in workshop HFSS. Yeah, save here. Okay. So that should have exported the scattering matrix, and we can double check whether he really did it. So he copied it into this directory, and it's in a touchstone file format. That's the default format for scattering matrices, scattering parameters. And let's have a look. And this is how the file looks like, and that can be read by ADS or MATLAB. And they have their files to import this data structure. So that's for the scattering parameters. And now for the fields. Karthik helped me with this. So if you have your solution, let's double check whether we have our field solution. I need to replot everything, but yeah, so this is how our field basically looks like. And now let's export it. So we can say we go to the menu bar, select HFSS, then go to fields, then calculator, and then you select quantity. You can, oh yeah, so you have a bunch of like pre-selected, predefined ways to export things like magnitude E, magnitude H. But if you want to export the electric field, all three components X, Y, and Z of the electric field, and the complex value of each three components, so that will be six scalar quantities describing the complex vector. Then you can select here E, quantity E. You need to smooth it. I don't exactly know what this function does, but I think you should be doing that. And once you've done that, you can just say export and calculate grid points, and then you can say in which box and which spacing you want your fields to export it. So let's just say from 100 millimeter, from -100 to 100, and spacing, let's say 20. And yeah, we should select the output file. I'm gonna name it e-export. Then we can say done and double check in the directory. And he wrote it in this directory. And we can have a look at the structure, but also MATLAB should be able to read this. So unfortunately, my screen is not wide enough, but basically what this file has is each line, you have the X, Y, and Z component of the point where you are exporting your fields. So here -100, -100, -100. And then in the remaining columns, you have the real part of the electric field and imaginary part of the electric field in the X coordinate, and then real and imaginary of the Y coordinate, and then real and imaginary of the Z coordinate. And yeah, and this data then you can use further in MATLAB for whatever purposes you need. It takes the export, especially when you have many points, can take a long time compared to, let's say, CST. And the reason for that is because, because the inherent, because of the mesh structure. In CST, you have orthogonal grid, and you can export very quickly on those grid points. But HFSS, because it has a tetrahedral grid, and you want to export on a Cartesian grid, you need to interpolate the field values at each point that you give in. So that's why it can take a little bit, it can take a long time if you are exporting on many points. But eventually you will do it. But that's like if you have many points, then maybe try to export it overnight. So that was the export, and now we can talk about co-simulation for single coils and arrays. So let's start with single coils. So let's have a look at this simple image example. So what we simulated so far is like a single loop. And we looked at the reflection coefficient or the impedance that we get when we excite it. But actually what we need to do in the experiment, every MR coil is usually matched to 50 ohms. And this we achieve with a matching network. And that matching network transforms the coil impedance, which usually has a small resistance and a high imaginary part, and it's usually inductive. So it transforms this impedance to 50 ohms. And for that, you need usually 2 degrees of freedom. One way to do this is by using fixed value capacitors to match to 50 ohms. Another way to do it by co-simulation and by do this matching in a post-processing step. So now let's try this matching in the post-processing step. Let's open, because up to now we only discussed the results from the previous workshop. Let's create a new is everyone still there?
Yes.
Any questions so far? Okay, I'm going to continue. Let's just take the perfect electric conductor, because this is going to give us the fastest solution. And right now at this point, it's like only for illustration purposes, so we are not interested in like having very precise results. I think I need to rerun this very quickly. Let's give it 3 iterations. Okay. Analyze all. All right, we have the solution now. Now let's have a look. Let's delete all reports and let's create a new report, this chart. New report. Yeah, and that's the result that we got before approximately. So this is the impedance of of the coil that we see when we look into the coil port. Let me just show it again for hide in all views. We can also hide the field. And hide the mesh with visibility. Okay. So this is our excitation, port 1 here. And we are exciting basically a ring of copper. And yeah, I mean, this is shorted. So first of all, we expect a low resistance, and we expect it to be inductive. And yeah, because there is no capacitor, and because we're going to create a magnetic field. And this is basically what we see here in the results. So we have a very low low resistor, and we are inductive. Maybe if we plot the Z parameters, it should give us the same result. We can probably create a rectangular plot, polar plot maybe, of the Z parameters. Yeah, and you can see it here. So for the Z parameters, we can see the angle and the magnitude, but I want real part and imaginary part. Let's see how we do that. Rectangular plot, Z parameter, none. No. Okay, let's do imaginary and real. So real part is about 17 ohms, and imaginary part is about 320. So it kind of, I mean, I don't know whether that's 100% correct. The real part seems a little bit high, but more or less like we are in the ballpark. Probably we should have run like more iterations, but for this purpose, it's going to be fine. So now what we want to do is match it. So we're going to do it in post-processing. And as Karthik showed me, we're going to insert a circuit design. We just choose none, workflow. And then we're kind of in a schematic plane here for the circuit design. We can see we added it to the tree, to the project tree circuit. And now we can just add, we can just select the model that we computed, and we can just drag it into the schematic workplace. You can see it here. And now I don't see what I want to see. Okay, no. Yeah, so now we can add an interface port here. And select it and say microwave port, select microwave port here. And we can see it's like a 50 ohm impedance, but we need to excite it somehow. So we expand the circuit and we say, we right click excitation, configure sources, and then we can say add to selected port. Let's select a voltage of 1. Okay. So this is the reflection or scattering matrix or reflection coefficient that we simulated from before. And we can connect this to the excitation port. And then we need to set up an analysis. Add next. So if we right-click in the circuitry, we right-click on analysis, and then go on add Nexum solution setup, say linear network analysis, and then yeah, then we can. I think I had this already before pre-selected, but you need to basically add a frequency step, and this was already here, 123 megahertz. You can edit it, and yeah, so this is what we want, because our original simulation was also 123 megahertz. But if you wanted, you could put in a different frequency here, which is like not needed here. But if you had like if you simulated multiple frequencies, then you could select like what frequencies you want to excite. So okay, and now let's see. Let's analyze this. And I hope he did it. Yeah, he did it. So then we can have a look at the results, create, let's say, Smith chart, S parameter, and we can see if we, if our circuit looks like this. So we put a 50 ohm port to our excitation port. We get basically, we get what we should get, and that's the same result that we had in the original simulation, because the original simulation uses also only 50 ohm sources. But what we now want to try to do, so this is only kind of a verification step. What we now want to try to do is to try to match it to 50 ohms. So this we can do by usually we can do this hopefully by adding 2 capacitors. And then if you look here at the component libraries, groups, then we can find capacitors. And we can place this here. I hope I can turn it somehow. Flip, horizontally, rotate. Yes. So then we need to connect it. And let's see what happens when we add a parallel capacitor. So we need to find a ground somewhere.
Ground is up top.
Okay, I see. Thank you. This is a little awkward with the rotation, but it works. So right click, you can say rotate. All right, now, so now the capacitor by default is set to 1 picofarad, and it's in parallel to the source and the coil. So let's see what happens when we rerun it. And before rerunning it, I think we need to delete results, analyze, and he's running. He's finished now. And now let's have a look at the Smith chart again. New report. Oh, we should have written down the value from before. Angular magnitude. Yeah, let's write down the value of this, and then so we can. There's a like smarter way to do this, but like the the fastest way right now is just to write down the values and try to find the capacitor that we need to reach 50 ohms. A 50 ohm real part. (13.28) and the magnitude is 0.98. Okay, there was 1 picofarad, and now let's try to change this. So we had 1 picofarad. Let's just say 5 picofarads. Okay. Delete all reports. Analyze. It did something, so we can plot it. Create Smith chart. New report. And you can see something happened. So now, yeah, we shot over the result. We added too much capacitance, I think. So there was 5 picofarad. Actually, what we should be looking at is the real part of the impedance. Let's just do that. Real part. And the real part is 278, but we know that we overshot. 278, and we don't know the real part for 1 picofarad. That just what happens if we do 3 picofarad here. And all right. Create rectangular plot. Z parameter real. New report. 264. Ohms for the real part, but let's have a look at the Smith chart. But the imaginary part is positive, so we are in a good way. But we are still too high. Let's do it 2 ohms maybe. So all these steps, what I'm doing right now, if we could have modeled the capacitor in the simulation itself, and each time we are changing the capacitor, what I'm doing in these steps, we would have to rerun a new simulation. And a simulation can take a day sometimes. Like if it's a complex model, it can take a day, and like you would lose so much time in like adjusting the capacitor. Whereas here, I do it only like in a post-processing step, and each time I change the capacitor, in this case, it takes me maybe 10 seconds. There's also a little smarter ways like ADS, you can do it much faster than here. But I hope you can see how time-saving this can be in most cases. So now we have 2 picofarads, and we can reanalyze. We finished now. Z parameter real part. Now we are getting closer. We are like 69 ohms. So that's close to 50 ohms. 69. So, but yeah, let's just keep it at 69 ohms. I mean, we don't have to get to really 250 ohms. Now let's have a look at the imaginary part, and there we can actually, let's just try to match it to 69 ohms. Maybe that's easier. For that purpose, let's just have a look at the Smith chart. Oh no, let's have a look at the Z parameter imaginary part, sorry. Create rectangular plot, Z parameter imaginary part, new report. Imaginary part is 635 ohms. So we need to cancel that. We want to cancel it with, let me show you. So there was 635, so let's write that down. Plus J 635. And now we want to cancel it by adding a capacitor in series. Rotate. And instead of playing around with the capacitor value, let's just compute the value that we need to cancel the real part. So there was, we know that the impedance of the inductor is J omega times L. So omega times L, omega is 2 times pi times 123 E6 megahertz. So that's the angular frequency, and the inductor omega L equals 1 over omega C times C. Yeah, it should be 1 over omega over 635. So we need approximately 2.04 picofarad in series to cancel the imaginary part. 0.04. Okay, let's hope that's right. And delete those, and let's reanalyze. Now we can create Smith chart, let's say. And we can see we landed on the, as expected, we landed on the real axis. So that should be approximately 69 ohms plus J0. Let's plot the real part of the impedance again. Real part, new report. Yeah, and it's about 69. So as expected. So we did this, like, we're not finished, like we need to get to 50 ohms, but you can see that, like, in 4 steps we can get kind of close. And this we have done all in post-processing, and we did not have to re-simulate the original, like, 3-dimensional simulation, which can take a long time. So now we have that, and we can also, because by having the circuitry, that will change the electromagnetic fields that we have in the 3D simulation. But we can, this result that we obtained from here, we can push back to the simulation. And we can do that by right-clicking on the model in the schematic and say push excitation. Or before we do that, let's actually compare. Let's see the field. Let's export the field at field calculator. So let's do something that we did before. Let's just pick the magnitude to have a single value. Push. or no, let's just do the electric field.
Jan, say if you want to do that, say copy to stack. If you want to do magnitude of H, just say copy to stack.
That's right, yeah. I'm gonna do it like this, but you're right, thank you. So if I wanted to have the mag E as Kartik said, you need to do copy to stack. But because it's a magnitude operation, I think it won't be exactly linear. I'm not sure. Or maybe it will be linear. No, I think it will be. Let's just do this. It's easier. Okay, magnitude E.
It would be linear, yeah.
We can export it, and then let's just export it at the point 0. In the origin, output file name, we can call this unmatched, because right now the coil is not matched, and we can export it to the workshop folder. Okay, done. Let's have a look if it's there, F unmatched. And again, it gives us X, Y, Z, and the value at the origin, the magnitude of the E field. So now let's, because we matched now this coil in the post-processing, and we can say here, we can say push excitations, and that will take the circuitry that we have in this circuit diagram, and it will basically attach it to our 3D model as if we had this matching circuit here, and it will update those results. So right now it will normalize the field. So let's see if this is really the case. And I did not try this before, so I hope it will update it. Let's again export the fields now that we pushed the excitations. So we have the magnitude E selected already. We can say export, and let's export it again at the origin. Okay. Name cannot be empty. So now this is matched. Done. And I hope it will give me a different solution. Yep, and the solution is different. So unmatched is 2.41 E plus 1, and matched is 2.42 E to the power of minus 0.1. But it's a little weird because I would expect the E field to be higher.
No, so basically I'm matching it. So at the center, you're maximizing the B field, I suppose. So the E fields get minimized, right?
Yeah, we should have exported the H field, eh?
Yeah.
I would expect both to scale the same way, though.
I'm not sure. Let's try the H field. That would make.
Okay, let's try.
Yeah.
I'm gonna, because I don't know how to unpush, but I'm just gonna reconnect it. And we're just gonna reconnect the circuit like this. Analyze. Let's double check the S parameters, and we are again at the original. So now we can push the results again. Push excitations. So now we should be back to the original without matching network. So if we now go to results, oh no, sorry, fields, calculator. Let's do mag E for now, just to see whether that's the same. And export it again at the origin. which folder did I save it in? Calculator, export, workshop. Okay. What's happening here? Oh, we maybe get an error message. Oh, doesn't export anymore.
What are you trying to export?
Again, the same thing, but he doesn't do it.
Yeah, go to results, fields calculator. Yes. Choose a different name. Export, Jan.
Now he has it, yeah. Strange. Anyway, so this is what we have unmatched. Let's compare it to the previous unmatched. Wait, it's both different.
Saw something in the warning message saying that like the number of simulation passes did not converge. So maybe.
1.25 is half of it.
Yeah, no, it's not even half. Like, look at that. It's around it's e power minus 1. Here it's e power 0. So it's an order of magnitude higher.
Oh, yeah. All right, that is a little weird now. Okay, I don't know how this. Maybe I should look into it a little further. But oh, yeah, I know why. Because of the voltage.
Yeah, I was going to say that. Yeah.
Yeah. Oh yeah, because in linear excitations, because we set here 1 volt, and that does not mean that the power is 1 watt.
It is not. So yeah, we need to scale the power. So it's 50.
Okay, so anyway, that doesn't matter. But let's just compare. So now we have one watt unmatched, and we this is not relevant. So this is our result that we are going with. Edit with them. This is 1 watt unmatched, is the E field. We can also plot the B field. HFSS fields, calculator. Let's also do the H field just to check. Okay. Then we have the H field here at the origin, and now let's go back to the simulation and let's match it. So we insert the circuit back that we had before. I can delete all the reports. I need to reanalyze again. Let's double check if we really, if we matched this chart, new report, and yeah, we matched it. So now we inserted this circuit, and now let's re-export again. So option, sorry, HFSS fields, calculator. Now we have the magnitude H. So this is matched. Again in the origin. Let's see if we have it. If we have it matched one. So I expect this file, this value to be higher than unmatched. Let's have a look. Unmatched H1. Oh, it didn't push the excitations. Now this is exactly the same.
You push the excitations.
Oh, I didn't push. I forgot to push the excitations. Okay.
Yeah.
Sorry about that. Okay, we need to. So we have now the circuit. We checked the S parameters. Looked close to 50 ohms. And now we have to push the excitation back into the 3D domain, 3D model. So we say push excitations. Yes. And now we go back to our 3D model. And now the value should be updated. And hopefully now I can show you what I wanted to show you. So we have the H field in there. Matched. Yes. Yes, now finally it's different. So the matched H field is much higher by 2 orders of magnitude higher almost compared to the unmatched case. And let's just for fun, let's have a look at the HE field, but I think that should be the same relationship. Copy to stack, export, matched E. Okay. And the matched electrical field compared to the unmatched one. Yeah, you're right, it's lower actually. Which I don't think it should be, but yeah, we can see that things are changing.
It might be that like it was just the simulation was just one pass, right? Like maybe it's not optimized. So
let me matched, match, unmatched, unmatched one. Let me just export again the E field. Okay, reanalyze. Reanalyze. Okay, we did that. Create model. Let's chart. Okay, now we are matched. Now, okay, this is the last thing we're going to do because I see it's already 3 o'clock. I'm sorry about this. So push excitations. And now going back to the 3D model. We can export the fields again, calculator. So magnitude is right. And we're going to call it unmatched E. Done. Yeah, it is like that. Yeah, we need to think about this a little more, I guess. But so really the unmatched E field is higher than the matched E field, which doesn't make much sense. But yeah, I'm sorry, but I would have to think about it for next time. I think we are already like running over time. But in any case, you could see how we can like from the 3D model, what we simulate in the 3D model, it like uses finite element method, taking the result, taking it to a circuit simulator, and this one uses only like currents and voltages and the concept of impedances or reflection parameters, and you can then compute like a different reflection coefficient for the 3D simulation, and update the result in the 3D simulation and change in this way the electromagnetic field. In this case, because it's only a single channel, it's gonna be only a scalar factor, a complex factor that you multiply the field globally with. But in an array situation is different. It can be like a matrix multiplication. But we get back to it the next time. But yeah, I'm gonna try to clarify the problem that I saw with the E field and H field. But let's take a break. Let's say until 3:15, if that's okay for everyone.
Yep.
And I'm gonna stop recording and see you back at 3:15.